Integration. So now we're going to get into more what integration is. So what do antiderivatives have to do with integration? It's one way of integrating. It's one way of doing the process what's called integration. It's probably the most common way, finding the antiderivative. Okay. There are a couple different ways to integrate. So what is integration? Right? We talked about last semester, we talked about derivatives. Derivatives were finding the slope of the tangent line at a certain point, right? That's what derivatives are. What is integration? Integration is right here, that first sentence. It's the process of finding the area under a curve. Finding the area under a curve. That's what integration is. Okay? So when we integrate, we're finding area under a curve, under a function, under f of x or whatever the function is. Okay. So one way to do that is by using antiderivatives. Okay. Another way, so we've been doing the process of finding an antiderivative, which next week we'll talk about how we use it to integrate. Today, we're going to use something called rectangular or trapezoid approximation method. Another word for it, another is Riemann sums. Riemann is the person who discovered this, how to do this. Newton kind of was the big guy on derivatives. Other people came in with integration. Okay, so one of them was Riemann. He came up with Riemann sums, which are rectangular or trapezoid approximation methods for finding area under the curve. Okay, so start out with this. So it's not blue on your paper, but it is on mine. If I look here, this is a function that goes from 0 to 8 on the x-axis, right? The blue, you can see, it's not really a curve, right? It's not really a curve. We really don't see functions like that. But if we did have a function like that, we could use rectangular approximation for it. So if you were going to find area under the curve, what would you do? So right now what I want you to do is find area under the curve for these two guys. Approximate it. What would area under the curve be for each of them? Okay, so I want you to do that. So what do you get? How much area do you get under this curve here? You guys have done that before. You guys have all found area of anything, right? I'm more interested in how you did it, right? Each of these shapes isn't a rectangle, isn't a triangle, isn't a trapezoid, isn't a square. It's kind of a irregular shape, right? How did you find area? What's the easiest way to find area of either of those green things? Divide them into smaller rectangles, right? I would say it's probably the easiest, right? Probably did something like this, right? You divided them here. Area of a rectangle is pretty easy, right? Area of a rectangle is pretty easy. It's just base times height. So for the first one, the base is 2, the height is 2. 2 times 2 is 4, so this area is going to be 4. Area is 2, height is 3, 2 times 3 is 6, and so on and so forth, right? That's how you pretty much did it. That's what Riemann said. Riemann's like, if I'm finding area under the curve, it's probably easiest to do that, to break it up into shapes that I know and to find area under the curve. Okay? Problem is, not a lot of our functions look like that. A lot of our functions look like that, right? These two guys, right? They're curves. So what I want you to do is use that to try to approximate. You're not going to get exact, but approximate. Use that method to approximate each of those. See what you get from 0 to 8. Use the method that you did on the first two to estimate. So you're just trying to do the best you can. It's an approximation. It's not going to be perfect, right? Because there's no way you can get rectangles to fit in some of those, right? You're going to go over, right? The green is the part where I need the area. But some of my rectangles go over, some of my rectangles don't cover, like there's missing parts, right? You just do the best you can, right? That's why it's called an approximation method, right? It's called an approximation method. It's not perfect. Okay? I got around 27 for the first one, and I got around 26 for the second one. It's an approximation. Okay? This isn't the correct answer. This is just my approximation of using rectangles. That's what Riemann said. Riemann's like, I can approximate it by using rectangles or trapezoids. Later we'll use trapezoids to find area under the curve. Okay? That's integrating, right? It's one of the more primitive ways of integrating. Okay? So here is rectangular approximation method, aka Riemann sums. Riemann sums. So it kind of explains what we just did, right? It kind of explains what we just did. So suppose we wanted to know the area of the region bounded by a curve, the x-axis, and the bounds A and B. Okay? Anytime you're finding area under a curve, there's always a bounds. Where do I start? Where do I end? Right? The first step is to divide the interval into subintervals, slices. Right? We can then draw rectangles using the width of each slice as the base. The height is determined by the actual function. Okay? So there's three types of rectangular approximation methods. There's left rectangular approximation method, LRAM. There's right rectangular approximation method, RRAM. And there's M rectangular approximation method, MRAM. Okay? There's three types. We're going to look at those three. So, looking at this example here, look at the first one. Which part of the rectangle is touching the blue? Which part of the rectangle is touching the blue? The left top, right? The top left. Only the top left. You look at top left, top left, top left, top left. Top left of every rectangle, right? That's called LRAM. Left rectangular approximation method. That's an example of LRAM. Okay? Now look at the second one. Which part of that is touching the blue? Which part of the rectangle there is touching the blue? The middle, right? The middle here. That's an example of MRAM. Okay? The total area under the curve is then approximately equal to the total area of all the rectangles. Which graph gives a better approximation of the curve? Why? How could it be determined? How could it be further improved? Well, it's the same curve, right? It's the same exact curve. So now find the area. Find the area of the rectangles. Find the area of the rectangles. What do you get? Are they the same? Are they different? So the first one is just rectangles, base times height. So I got 22. The second one is a little bit tricky because some of the heights aren't clear. Like the height of the first rectangle, I think it's 3.5. So 2 times 3.5 is 7. Same thing with here. The height of the third triangle or the rectangle, I think it's 2.5. I think it's 2.5. So 2.5 times 2, 5. This one's a little bit harder because it's right under 4. So I said approximately 8 because if it's 4 times 2 is 8. So when I added them all up, I got approximately 26. There's a difference there. One's 22 and they're 26-ish. Which one do you think does a better job of finding area under the curve? So my question is the true answer, is the area under the curve closer to 22 or is it closer to 26? Why? You're right, why? This part right here, right? Big chunk missing, right? And then over here, we got a big chunk going above. And then there's a big chunk here and there's a big chunk there, right? Big gaps. This one still has gaps, right? But not as many. So I agree. The true answer is probably closer to 26. Okay. All right. Okay, so now we're going to do one together. We are going to do one together. So these are the 3 steps. Okay, so first thing we got to do is divide or partition the interval into however many subgroups. They'll always tell you how many subgroups they want. Okay, so this guy here, we are going to use RRAM and LRAM. So it goes from 0 to 8, right? The interval goes from 0 to 8. We have to divide them into 5 rectangles. It doesn't say the rectangles have to all be the same width. So it's really up to us into how we're going to divide them. But we're going to have to use RRAM for the first one and LRAM for the second one. Okay, sometimes they'll say use equal subintervals. That means the width has to be the same. This one doesn't say that. This one just says use 5 rectangles. Okay, so if we're going to use RRAM, that means the right side has to touch the blue line, has to touch the function. Okay, so there's many ways to do this. I just have to have 5 rectangles. Okay, so the first one, let's see. It's my first rectangle. Touches the blue on the right side. Let's see, this guy right here touches the blue on the right side. I'm just going to use the dots because I think there's 5 dots. One, two, three, four, 5. Yeah, 5 rectangles. The right top touches the function. Okay, that's RRAM. LRAM. Okay, so LRAM, the left top touches the function. So the first rectangle is going to be like that. The second rectangle is going to be like that. I'm just going to go from dot to dot. Oops. What is this? LRAM, sorry. Did this wrong. the left top left touches each of the dots. Okay? Same function, just one's LRAM, one's RRAM. We don't have to find the area. It doesn't say find the area, it just says illustrate it. That's the difference. Okay? So that's how you do LRAM and RRAM. LRAM, the top left touches. RRAM, the top right touches. MRAM, the middle touches. Okay, so we're going to do an example where we do one of each. We're going to do an actual example, one of each. Okay, so they've given us 3 graphs. They're all the same. We're going to use 4 rectangles to approximate the area under the curve, which is y equals x squared minus 2x plus 2. We have to go from 1 to 3. So the bounds go from 1 to 3. So from 1 to 3 for each. We have to use 4 rectangles. If possible, I like to use equal width rectangles. So if I need 4 rectangles, what width should they be? 0.5, right? Because if I make them 1, then there's only room for 2 rectangles. But I need double that, so I'm going to do 0.5. So 0.5 is going to be the width for all of them. Okay. The first one is LRAM. Okay. So the first one is going to go from there. Top left has to touch. Top left has to touch. Top left has to touch. Each of those rectangles, the top left corner touches the function. There, 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 and there. They all touch the function. If the top left doesn't touch the function, it's not LRAM. Okay? Now I got to do RRAM. RRAM is the top right touches the function. Okay? So that one is going to look like that. That. That one's going to look like that. The top right touches the function everywhere. Okay. The next one is MRAM. The middle is going to touch the midpoint. So the middle of, so this one here, so the first rectangle is going to be from 1 to 1.5. That's the width. Halfway is 1.25. So where does 1.25 hit, right? It hits right there. That's the height. That's going to be the height of my first rectangle. The midpoint of my next one is going to be 1.75. That touches right there. That's going to be the height of my second rectangle. The next rectangle is from 2 to 2.5. The midpoint from 2 to 2.5 is 2.25 right here. that is going to be the height of my third rectangle. And then the last rectangle is from 2.5 to 3. Halfway from 2.5 to 3 is 2.75 right here. That one touches there. That's going to be the height of my last rectangle. Okay. Use a different color. So this is examples of LRAM, RAM, and MRAM. Okay, the dot's in a different spot. That's the difference between them. The dot's in a different spot. Now what you're going to do is find the area of each of those rectangles. Find the area of each of those rectangles. Okay? That's what I want you to do. The last thing we're going to do today. We probably won't even finish today. Find the area of each of those rectangles in the box. There's a box in the back. Or you can do them underneath. If you have room underneath, you can do them underneath, wherever you have room. What's the area of each of those rectangles? I know the width of the rectangles is all going to be 0.5, right? The width is all going to be 0.5. The base of them are all 0.5. So you got to find the height of each rectangle and multiply. And then when you got those, add them all up. So I have a question on some of these. Some of these are like, the heights are pretty easy, right? Like this guy right here, this height is 1, the base is 1, right? Or sorry, the base is 0.5, the height is 1. What's the height of this guy here? Well, see, we don't want to approximate because we're already approximating, right? We're already approximating the area under the curve. I don't want to approximate again. I have to actually find the actual area or the actual height of that guy. I do have a method. What is the method for finding the actual height of this guy? There is a way to do it. Because if you approximate too many times, it's going to be off. We're already approximating the area under the curve, right? So we don't want to approximate again. Because some of these, right, even here, I don't know what that height is. I don't know if that looks like maybe 1.5. I don't know. How do I find area? Plug in the value for the, yeah, exactly. We have the actual function right here, right? That determines height. This is going to determine your height. So if I want to find the height of this guy here, 1.5 determines that height. So I plug in 1.5 to this guy over here. So if I plug in 1.5, for x, 1.5 squared is 2.25. 2 times 1.5 is 3. 2.25 minus 3 is negative 0.75, plus 2 is 1.25. So this guy is actually 1.25, not 1.5. Okay? Some of these you will have to do that because the height is in between two values. So you don't want to if you have the ability to, we have the ability to. We have the function right there. The function is right there. That's how you're going to determine the height. Same thing here. Same thing here for this rectangle here. It looks like 3.5 height, but I want to be sure. So I'm going to plug in the value, the x value, which determines the height. That's 2.5. I'm going to plug in 2.5 and see what I get. To the original equation, to f of x, which is at the top. Well, 25 squared is 625, so 2.5 squared is 6.25. 2 times 2.5 is 5, plus 2. 6.25 minus 5 is 1.25, plus 2 is 3.25. Okay? That's what you're going to do. So we'll finish this tomorrow. Okay? First thing when you come in, you're going to do this. You're going to finish that. Find the heights.